Hello, good morning all. Yesterday we were discussing, we started with wave mechanics. Today also we are going to continue with this particular topic, that is the wave mechanics, and we'll try to see different postulates that will be there, and that will be very instrumental in doing overall quantum mechanics. Okay, so without wasting time, let us start. Again, there's a problem. Just give me a minute, okay? So just give me a minute so that people would join in, and then we will start. Okay, just give me a minute. Okay, so wave mechanics, which is in which we are discussing right now, Schrödinger equation, and in particular, sooner we are going to start with the time-independent Schrödinger equation in different potentials. Okay, so yesterday we started with this particular topic, and we saw a few of very important things. Let us take a little bit of revision kind of thing. Okay, let us first take the revision kind of thing. Okay. So yesterday we have discussed a few of the points that are very important for your quantum mechanics. The first point that we were discussing was Schrödinger equation. See, yesterday also I told you, like for example, whenever you are doing classical mechanics, you know that you know that a motional law of mass m moving under the influence of force in one direction, that is if I am describing a particle in a single degree of freedom, I know that I can write that net force on this particle along x-axis is equals to mx double dot. Okay, now question arises that what would be the equation or motional like equation which will be governing the quantum mechanical objects in general. Okay, understand that in quantum mechanics there is something called as wave particle duality. That is uh, that is both, I'll write it here, both light, that is you can write it as radiation, and matter, that is let's say for matter I'm saying, let's say electrons, atoms, etc. Both of them manifest wave-like and particle-like. Particle-like properties in different scenarios. In different scenario, by which I mean that uh, the, depending upon the experiment, depending upon different scenario experiment, you will see that a certain particular thing, let's say light or probably matter, displays a wave-like characteristic, and for certain experiment the same particular light or let's say matter behaves as if it is a particle. This particular property is called as, this is referred to as wave particle duality. I'm not getting deep into it, but just a little bit of revision that what we did yesterday. The second thing we did, so if as I told you, given two different experimental setups, so I'll write, given two experimental setup, you can either have wave-like characters or you can have either light-like characters. For example, when you say that I'm discussing about Compton experiment, so it can only be explained on the basis of the particle nature. Okay, but if you consider the young double slit experiment, it can only be you can say understood, or it can only be understood, or you can say it can only be uh, properly comprehended if you assert that it shows a wave-like character. So this particular thing, that either a particular experimental situation would refer to a particle-like character or wave-like character, is called as the complementarity principle. So this is something that I'm going to write. So given in a given experimental situation, I'll write if wave properties are detected. If wave properties are detected, then simultaneously it is not possible, it is not possible to describe the situation, or you can describe the situation using particle behavior. Okay, so this is one thing. Okay, and vice versa. Okay, so what does it imply? It implies that this mutually exclusive behavior uh, is called as the complementarity principle. Is called as the complementarity principle. Okay, so either it is going to display wave-like character, or, and this particular complementary principle has been famously given by Niels Bohr. Okay, so this is one thing. Now you see, so for example, if we are saying that arrival of photoelectrons, or you can say, let's say photons only, let's say photons, uh, arrival of photons at detector screen, they can only be understood if I am taking photons not as a wave but as a particle. Okay, so we cannot think them as wave here, we cannot take them as. However, if you are doing an interference pattern, okay, so let us say in same double slit experiment, if I'm trying to do in the double slit experiment, if I consider the interference pattern that is observed, it can only be explained on the basis of wave-like character. So I hope you understand that if wave-like characters is exhibited, then it cannot simultaneously exhibit uh, a character of particle, and if certain experimentation um, holds, or you can say uh, actually describes a particle-like behavior, then it cannot express the wave-like character simultaneously. So one has to understand that there lies a complementarity in exhibition of this wave-particle duality. Now, a little bit of understanding. A few books have done this, so I'll do it accordingly, according to the books only. However, I am of the belief that since we are preparing for an examination, a direct know-how of Schrödinger equation would do. But let us do for the sake of doing it. Okay, a few things that you need to remember from your standard 12th. The first thing is, according to the de Broglie hypothesis, according to the de Broglie hypothesis, we know that with respect to a particle, with respect to a particle, there is a matter wave. There is a matter wave. Okay, and this particular matter wave, let's say the amplitude of this matter wave is given by some function psi of x comma t. Now the natural question arises as to how this particular psi as a function of time or space evolves. Okay. Also, it leads to a question that does it this particular the amplitude of matter wave, does it satisfy the famous wave equation? Okay, so both of these questions arise. Now it happens that this particular psi is a function of x and t satisfies something called as Schrödinger equation, which was developed by the name of the physicist, which is Erwin Schrödinger. Now recall, since the matter waves are dispersive, so therefore they don't uh, they don't satisfy uh, the famous what you can say the famous uh, classical wave equation and equation, which is 1 upon c square del square upon del t square is equals to, let's say in 1 degree of freedom, if I'm writing, I'll write this. So it does not satisfy this classical wave equation. What some textbooks have done, they have tried to use this result of de Broglie hypothesis, and they have inferred the time evolution of wave function of a free particle. Let us try to do that. Now, understand that when when I'm saying that electron is particle, and let's say it is a wave, how to represent this particular particle? So it is assumed that it is nothing but it is a superposition of various waves of different wave numbers or frequencies. This particular formulation is referred to as wave packet. Okay, so this is something that we are going to see a little bit of in detail later on, but right now just think about it. That that just take it as a fact that a particle, when it has to be, it is supposed to be represented as a wave. It is represented as a wave packet, which is nothing but it is the superposition of various waves. What sort of waves? Waves of different frequencies, you can say, or you can say wavelengths. Now, suppose at t equal to 0, the wave function of an electron is a wave packet psi x. Being a wave packet, I can express it as superposition of different wavelengths. You can say here I can write monochromatic uh, uh, monochromatic waves of different wavelengths. Okay, so this is something that I can do. Now, if I'm saying this, if it is a superposition, had it been a discrete case, I would have used integral, I would have used a summation sign. But since I'm saying, uh, uh, I'm taking it as a function, so psi as a function of x comma t at 0, I have written that this is a wave packet. It implies what? It implies that we have to take the superposition of all possible waves of different wavelengths. Having taken different wavelengths means having taken different case. Okay, so this is one thing. Okay, now this is one thing. Now you see the de Broglie hypothesis. Okay, so the de Broglie hypothesis suggests that this particular thing, that is the what should I say, this particular thing, which is, let's say, omega, or let's say uh, you can say momentum also. Momentum is related to h to k by this, or when we have to see according to de Broglie hypothesis, the angular frequency okay. And if you're getting confused with this, don't worry, this is a Fourier transform. This is a Fourier transform. Okay, so this you remember right now, otherwise you'll not be able to, because something of this thing we are going to see when we are going to discuss the wave packet. But right now just take it as a concept that we have taken a Fourier transform over different case. These case means what? We are in momentum space, or you can say we are here in the k space. So having taken different case means having taken different wavelengths. So basically, different wavelengths, you can say waves of different wavelengths, when they superpose, basically they're going to describe a particle in coordinate space. Now you see de Broglie hypothesis, the angular frequency of the wavelength of the wave packet, you can say, uh, is related to the energy. So I can write E is equal to h ket omega, or simply E upon h ket. And having said all these things, I can relate it to P square upon 2m h ket. And since I know that P is related to K, so I can write it as h ket square divided by h ket. So that will be simply this, so h ket K square divided by twice m. Okay, this means what? This means this means that each wavelength mode, you can say each wavelength mode oscillates with oscillates in time according to e की power iota kx minus omega t, and instead of omega you can write this e की power iota kx minus iota h ket k square upon twice m t. So if I use this particular thing in C, Here I use what? Here I use that it is not at t equal to 0 I was using it. But in general, if I use time t, then this would be the better way of expressing a wave amplitude. So e ki power a wave, you can say e ki power iota kx minus omega t. And instead of omega, if I use this, so this will give me at any particular time t, the at any particular time t, the wave function, or you can say uh, the function which was representing the wave packet can be written as integral dk upon 2 pi e ki power, sorry, you can say here e ki power iota kx minus iota h cat k square upon twice m times t, and then this is it. This is one thing. Okay, so let us denote this particular scenario, and this particular 1 on 2 pi comes because of the Fourier transform. We have done some lectures on Fourier transform. Okay, so I'll say that my dk upon 2 pi is nothing but let's say it is square bracket dk, one thing. Okay, so I'll write psi as a function of x comma t is integration dk in square bracket. You have this, and then you have this iota kx minus iota h cat k square. Okay, this is one thing. Now you see, there is some important thing that you need to see. This particular thing is function of both x and t. So what I would do, I would try to differentiate it with respect to t. So when I differentiate it with respect to t, this particular derivative will go inside the integral sign and will differentiate partially with respect to time. And what it will lead me to, it will lead me to this. All things you have, there's some k square also. So k square would come. I'm not taking k square outside because this integration is done with respect to k. This is one. Also think, if I try to differentiate this with respect to x twice, then what I'm going to achieve, that I'm directly writing, I'm not going to take a step out of it, because if you differentiate it twice, you're going to get minus k square. So I'm writing it here, k square, negative I've taken outside. Or you can say this entire thing as a, if you don't like this writing time and again, write it as omega as a function of k. Now, if you just relate these two, if you just try to relate these two, you are going to get a linear partial differential equation, which is iota del h upon del t is equals to minus of h cat square upon twice m times del square psi upon del x square. Understand that this particular thing represents what? This particular is represents the evolution of wave packet, you can say, or you can say wave function mathematically. What does it represent? It represents the wave function of a non-relativistic, you can say we have not taken any relativistic considerations while doing so. Obviously, when I was discussing about it having some momenta, it having some energy, I would say wave function of a free non-relativistic particle. Why free? Because it does not contain any potential term. It does not contain any potential term. One of the most important observations of wave in general in electromagnetic wave, also you're going to see the same thing, is that when I was differentiating this psi with respect to time t, when I was differentiating this psi with respect to time t, you can say if I use this particular thing, k square iota h get upon 2m, this entire thing was equals to omega as a function of k. So when I was differentiating once with respect to t, I got all these things here. So it is equivalent to multiplying with minus iota omega k. Okay, I'm just again trying to show you what I want to say. So let's say here it is, just showing you here. Let us say if I'm saying if I'm differentiating this particular thing, this is what it was. Remember, omega is a function of k. Okay, if I differentiate this particular thing with respect to t, what it is going to show. Sorry, this iota would come. Okay, iota kx. I'll write iota here. Okay, so that you don't get confused. Okay, so if I differentiate it with respect to t, it so happens that this particular thing comes out minus iota omega and this. So if I take a derivative with respect to time, it is equivalent to multiplying the integrand by minus iota omega. So your del by del t as an operator, when I see it in this particular k space, or it is usually also referred to as the Fourier space, this del by del t is equivalent to multiplying the integrand with respect to minus iota omega. So the del by del t in general, in k space, if I want to express this, it is equivalent to writing, or it is equal to multiplying it is equal to multiplying by minus iota omega as a function of k. Similarly, if you're going to see what is del by del x, what del by del x is going to institute in k space, it is equivalent to multiplying by iota k. So having seen all these things, so de Broglie hypothesis de Broglie hypothesis with the energy relations, that is E is equal to h cat omega, and the momentum relation, that is P is equal to h cat k, leads to a correspondence that is del by del t is equals to so and so. In k space, it is equals to minus iota omega t. It is like del by del t, doing del by del t is equivalent to uh, multiplying the integrand by minus iota omega in k space. And if I'm doing a del by del x, it is equivalent to multiplying by iota k. What we do in quantum mechanics, one of the postulate is that the classical observables such as position, velocity, momentum, energy, all these classical observables, are represented in terms of operators. Therefore, we introduce two of the operators. The first one is E cap, which is equivalent to writing iota h cat del by del t. and the other one is p cap. In one dimension, I'm writing minus iota h cat del by del x. Having introduced both of these things, the Schrödinger equation for a non-relativistic free particle becomes this thing. Please do remember, this is the Schrödinger equation for non-relativistic particle moving freely, as in it is not under any potential, moving freely. This is the first thing that you should understand. Now, had it been influenced by certain potential, let's say Vx, then this equation transforms to this equation. In the theory of quantum mechanics, this operator in this parenthesis is referred to as Hamiltonian operator. And this particular expression is called as the Schrödinger equation. For a free, non-relativistic particle. Now question arises that this particular expression we have derived using a matter wave hypothesis. Okay, we suggest that every particle uh, is actually you can say that with every particle there is a matter wave associated, and also we have extended it as a you can say motional law. So you can say that it is a kind of a equation that governs the quantum mechanical objects. Now, whether it is a correct physical law of the time evolution or not, it can only be said that it can only be predicted correctly if it has certain coherence with the experimentation. Although I'm not saying that we need not check the mathematical consistency while doing something, but one has to understand that we have given psi x a physical meaning. What is a physical meaning? We understand that every particle can be represented as a superposition of matter waves, of different waves of differing you can say wavelengths. Having superposed all those things, we understand and we conceptualize but that particular thing as a particle. So conceptualization of a particle in terms of wave function is one thing, and second thing is matter wave hypothesis. Having these two ingredients have supplied a quantum mechanical equation. Now, whether this is right or wrong, this can only be confirmed if whatever we are doing in mathematics has certain consonance with the experimental findings. Until date, it has never seen to be violated. So therefore, we assume, we, we say that this is a one master equation which governs the quantum mechanical phenomena. Or you can say it is one of those equation. It is one of that equation which correctly represents the evolution of the wave function as a function of space, that is x, y, z, and time t. More generally, understand it also iterated that why we needed a postulate. If you see that here E is operating over psi, it is equal to sum of this thing, which is I think p square by 2m plus b times psi. So it also renders an important result or important postulate of quantum mechanics, which says that each classical observable is replaced by an operator. Okay, so while you see that p cap in one dimension, that is in you can say along x-axis, is written as minus iota h get del by del x. Similarly, the coordinate is simply multiplying it with x. Let's say if I'm saying coordinate operator, that is x cap times psi x gives you x psi x. So all you need to do is, whenever you have to see what it is doing, you have to operate it over some wave function. This is how you do things in quantum mechanics. Okay. Now, yesterday also I emphasized on this particular point that in general, psi is a complex valued function, and it is psi mod whole square which represents the probability density. And a little bit of understanding I developed with regards to the collapse of wave function. I also told you that in quantum mechanics, we actually bother with something called as the expectation value. Why do we do so? As we know, let us say that there are n particles which are prepared in the same quantum mechanical state. Let us say psi x. But even if let's say I just try to measure positions, one has to understand that this particular position will be different. This particular position measurement would be different for different particles. In general, I'm saying, okay? So possibly you will have different outcomes. Why different outcomes? Because you know that after all, this particular distribution, this particular, you can say, the distribution of the position measurements distribution of position measurements are governed by psi mod whole square. So it is governed by the probability density. Let's say it is let's say Gaussian. A different particles. The particles have the probability of being anywhere in this particular space. If this is psi mod whole square, this is let's say x. What does this area represent? This area represents the probability of finding a particle. We don't know exactly where the particle is. So if we are trying to measure the position, we may get different outcomes. And since we get different outcomes, there is some important quantity that needs to be taken care of, and that is called as the expectation value or average value of observable in a particular state. So let us just understand what is this particular thing. So this brings me to a topic which is an important topic in quantum mechanics, and it is called as the average value, or you can say expectation value of observables in a state. So same, if we are trying to make position measurements, on on a large sample of, let us say, some particle, let's say electrons, prepared in the same state, let's say psi x. This I refer to as, in statistical terminology, an ensemble. As I told you, since this psi mod whole square follows a distribution, so this may possibly yield you different result. That is, I can say that this distribution of position measurement will be governed by psi x mod ka whole square. What does it say? It says that probability of finding a particle anywhere in space is psi mod whole square dx. So probability density would be psi mod whole square. So position measurements are said to follow a probability density governed by psi x mod ka whole square. This is something dictated by Bond's probabilistic criteria. If we are saying that it's not in 1D, let's say it is in 2D, and if one wants to find the expectation value of y, what does it imply? It implies I have to find integration y psi, I will write it here, x, y, z mod whole square dy. If it's not normalized, then I'll divide it by, if it is normalized, then there is no need to divide it by this particular thing. In general, always remember that if I want to write, the expectation value of an operator A, it is given by integration. Let us first take an example of, not directly, let us first take some example and then let us try to go through this particular theory. Okay, so let us first try to take, okay, I took an example earlier only. So, okay, I took one example before only. Let us try to take an easier example. If I want to find, let's say, my wave function is simply function of x. And if I want to find the average position, or you can say the expectation value of x in this scenario, it is equals to minus infinity to plus infinite x into psi mod whole square dx if it is in a normalized state. If it is not in normalized state, then you have to divide it by psi mod whole square. Let us for simplicity first take that psi x is normalized. So if that's the case, I can write this as this. Since x is a real operator, so I'll write it here. It is not going to matter much if I write psi star here and psi here, and this is it. Because psi mod whole square is nothing but it is psi star psi dx. And similarly, if I want to find it in 3 dimensions, and let's say I want to find the expectation value of y, this is equals to minus infinity to plus infinite. This would be simply y into psi mod whole square, which is I think x, y, z mod whole square, and this would be dy. Had it been normalized, then you don't need to divide it. Otherwise, you'll have to divide it by the normalizing constant. Now, let us try to find having said all these things, if this was expectation value of x, we got something like this, psi star x and psi. On similar lines, if I tell what would be px, it would be psi star minus iota h ket. You'll get del by del x here, and this is psi dx. So this particular integration, provided this psi is normalized. If it is not normalized, then you need to divide it also. Divide it by the normalizing constant. The similar interpretation, I'm going to write it for any operator. So for any operator A, if I want to find the expectation value, this would result me in finding this particular mathematical object. And right now I'm focusing on wave functions having a single degree of freedom. Okay, so I hope it is clear. Okay, so understand that in measurements, in quantum measurements, this particular theory of expectation value is necessary. So you can say finding expectation value is necessary. That is, we need to make repeated measurements on an ensemble. Ensemble means, let's say, if I want to say that I have a large sample of electrons, then each one of them should be prepared in the same wave function. And if I take a different measurements, then I'm going to get possibly different result. And I'll have to take an average value, which is referred to as the expectation value. Understand, this is not by repeated measurement. I'll write it here. By repeated measurement, We do not mean measuring the we do not mean measuring the uh, position of one electron. Okay, so if that's the case, then there's no point of repeating it, because if we repeat the same position measurement, then let's say in quick succession, if I'm doing it, then it is going to yield me the same result. However, on the contrary, if we measure if we measure the position of an electron in a state psi x once, we are more likely to get what? We are more likely to get a value of x for which you can say that psi mod whole square is large. So where a probability is large, only that particular value would be reflected. That particular value of x would be reflected. Compared to then value of x now only after repeating the measurement, only after repeating the measurement very soon or in quick succession, so repeating the measurement on an electron that has been found at x just confirms that it is at x. What do I want to say? I want to say that whenever it comes to quantum mechanics, we take averaged values because we understand that each of these values, each of these position measurement are governed by a probability distribution. They are governed by a probability distribution given by psi mod whole square. So repeating the measurement on the same electron will not serve the purpose. So therefore, we prepare an ensemble where electrons, all the electrons are prepared in the same wave function, in the same wave function state, or you can say in the same state. And then we repeat the measurements. If we don't do so, then it does not make sense. So understand, whenever I'm seeing by repeated measurements, this is not same as repeatedly measuring the position of one single electron. So therefore, in you can say in our quantum mechanics, one of the things that becomes very important is expectation value. I hope it is clear. So having said all these things, tomorrow we are going to start with real quantum mechanics, and probably from tomorrow we are going to also start with the probability current density. Let us little bit of introduction let me give you, and then we'll take it from here tomorrow. Yesterday, I was discussing with you that if I had normalized my wave function at time t equal to 0 with a normalization constant a, then this particular normalization constant remains constant throughout. I told you that this d by dt of integration from minus infinity to plus infinity psi mod whole square dx comes out to be equal to 0. That implies that if I have found the probability to be equals to 1 at a certain time, let's say t equal to 0, this particular probability would remain 1 even at any future time. In other words, if I say that my probability, or you can say, what is probability? Probability is doing psi mod whole square. It implies that if wave function is normalized to 1 at t equal to 0, that is initially, then it remains normalized, or you can say then it continues to have a norm of equals to 1 in all future times. This is referred to as the global conservation of probability. It asserts that the total probability of the particle being found anywhere in the space remains 1 for all times. Now, what happens is there is one important thing that is called as probability current. It so happens that the probability, that is psi mod whole square, if I say, it also flows as if it is a fluid. It flows as if it is a fluid. Okay, that is, it cannot have a jumping kind of situation. So you cannot say that your probability jump in binaries, or let's say in some sort of distribution, or you can say that it cannot jump. It is going to flow like a current. And there happens to be a local conservation of probability local conservation of probability, just like mass in a fluid. And we see that there is a continuity equation that we are going to see in this particular scenario. This is an important concept in quantum mechanics, which we are going to start off in the lecture number 3. From lecture number 3, you will come directly to the business. We'll try to do something called as the Ehrenfest theorem. I'm going to little bit digress over uh, get and brand notations, and then we'll start with individual, you can say, what you can say, individual potentials. I hope you're attending these lectures. If you're finding any trouble, please let me know. Till then, take care. Bye bye.